Section: Introduction. In this section, we delve into the challenges posed by the increasing complexity of machine learning models and the resource-intensive nature of their training process. The emergence of generative AI has led to the development of large language models, LLMs, that require extensive training periods, sometimes spanning months and involving hundreds or thousands of GPUs. For instance, the 70 billion parameter model Llama 2 needed 1,720,320 GPU hours to train. However, such prolonged training can lead to instability issues, as seen in models like Google's PaLM, where sudden spikes in loss occur multiple times during training, causing disruptions that necessitate stopping and restarting the training process. While previous studies have explored ways to mitigate training instability algorithmically, the root cause of this instability remains unclear. The stochastic nature of model training, coupled with the challenges of observing these effects at a large scale, makes it difficult to fully comprehend these instabilities. Additionally, conducting multiple training runs to pinpoint contributing factors is often impractical due to the high costs and demand for computational resources in data centers. One lesser explored factor that could contribute to training instability is numeric deviation. Discrepancies in numerical values between an optimization and its baseline can lead to errors accumulating over time, potentially resulting in loss spikes that necessitate resetting the model state. Quantifying this phenomenon is challenging due to the stochastic nature of training, which implies that some level of numeric deviation may be tolerable. However, determining the threshold at which training becomes unstable is a complex task. To address this issue, we propose a systematic quantitative approach to understanding numeric deviation in training optimizations. Our approach involves two main phases. First, we create a micro-benchmark to introduce variations in numeric precision within the optimization, and second, we analyze how these deviations impact changes in model weights using a data-driven approach based on Wasserstein distance. This methodology enables us to establish an upper limit on the acceptable amount of numeric deviation in a given optimization and helps us assess the effectiveness of existing techniques in this context. Our goal is to use this approach to evaluate cutting-edge optimization techniques and assess their potential to introduce unintended instabilities when training large models. As a case study, we examine the optimization technique flash attention, which is widely used to accelerate the attention mechanism in transformer models. While flash attention offers speed and efficiency improvements by optimizing algorithms, it may also introduce increased numeric deviation that could affect training stability. Specifically, we suspect that the inclusion of rescaling factors in flash attention could lead to unintentional approximations, resulting in a numeric trade-off that impacts training stability. By analyzing flash attention in the context of multimodal text-to-image tasks, we aim to determine the significance of numeric deviation compared to the baseline attention technique. Our framework allows us to quantify the impact of numeric deviation resulting from training optimizations and its downstream effects. Key contributions of our work include the design of a micro-benchmark to assess numerical precision impact, a data-driven analysis using Wasserstein distance to contextualize numeric deviation, and the quantification of model weight changes due to numeric deviation introduced by flash attention. Our findings highlight the importance of a systematic approach to understanding and contextualizing the effects of training optimizations on numeric deviation, enabling us to reason about potential downstream effects such as training instability that are traditionally challenging to measure. Section Summary. In this section, we delve into the challenges posed by the increasing complexity of machine learning models, particularly in generative AI, where large language models, LLMs, like Llama 2's 70B parameter model demand extensive training times, often leading to training instability marked by loss spikes. We introduce a quantitative approach to understanding numeric deviation in training optimizations, focusing on flash attention, a technique aimed at accelerating the attention mechanism in transformer models. By analyzing the potential numeric deviation introduced by flash attention compared to baseline attention, we aim to quantify and contextualize the impact of such optimizations on model stability. Section: Understanding flash attention. In this section, we delve into the concept of flash attention. We explore how flash attention works to speed up the attention bottleneck in transformers. Flash attention is an I/O-aware technique that aims to reduce the memory usage of the large similarity matrix typically used in the attention mechanism. By using tiling, recomputation, and an online softmax trick, flash attention calculates the matrix one tile at a time, eliminating the need for the entire large matrix to be stored in memory. The block size is determined by the size of the SRAM and the model dimension to ensure it fits inside the SRAM without the need to load, store from HBM. However, the online softmax technique requires global information about the matrix, so flash attention includes rescaling factors to enable consistent calculations when computing on a single block. While these rescaling factors introduce some extra computation per tile, flash attention improves timing performance and resource utilization, resulting in a 14% speedup for our text-to-image model. We then move on to our experimental methodology. We create a micro-benchmark to study the numeric deviation caused by flash attention. By numerically re-implementing flash attention and analyzing different numerical precisions, we can make optimizations not possible with the original CUDA implementation. Our micro-benchmark design allows for varying precision inputs and modifications inside the algorithm, unlike the current flash attention kernel that only supports FP16 and BF16 formats. We validate our micro-benchmark against the original flash attention kernel and develop a technique to compare the output of the attention matrix during model execution. By computing both baseline attention and flash attention each time attention is called, we can compare the output matrices. We also quantify the difference in model weights throughout training using metrics like max difference and Wasserstein distance. Analyzing the impact of flash attention during the forward pass, we find that numerical precision affects the output matrix, causing deviations from baseline attention. The numeric deviation decreases with increasing mantissa bits, indicating approximation errors with fewer bits. Comparing flash attention to baseline attention, we observe roughly 10 times more numeric deviation at BF16. Increasing the sequence length leads to more significant numerical deviation between flash attention and baseline attention due to the need for more rescaling with larger intermediate matrices. Section Summary. In this section, we delve into understanding flash attention, a technique aimed at speeding up the attention bottleneck in transformers by minimizing memory overhead. By using tiling and recomputation along with an online softmax trick, flash attention calculates the similarity matrix one tile at a time, eliminating the need for a large matrix to be materialized. While flash attention brings about a 14% speedup in performance for text-to-image models, it introduces additional computation through rescaling factors that may lead to numeric deviation, especially noticeable with varying numerical precisions and increasing sequence lengths. Section: Sweep algorithm changes. In this section, we leverage the micro-benchmark design to experiment with different optimizations to understand the effects of numeric deviation. We analyze several algorithm changes and their impact on observed numeric deviation. For each experiment, we vary the block area and plot the maximum difference between attention matrix outputs. Swapping the order of block dimensions leads to larger numerical differences between flash attention and baseline attention. Larger block tile sizes result in smaller numeric deviation because fewer rescaling calculations are needed with larger tile sizes. While flash attention may cause numeric deviation during a forward pass, our goal is to determine if this affects model training and contributes to training instability. We measure the model weight difference between models trained with baseline attention and flash attention using two metrics, max difference and Wasserstein distance. These metrics show that models trained with flash attention converge to a different model than those trained with baseline attention. To understand the significance of weight changes due to flash attention, we compare weight differences during training under different scenarios. We find that the rate of change of weight deviation for models using flash attention is comparable to or less than the deviation from different model initializations. Additionally, the rate of change of weights with different precisions, FP16 versus FP32, is higher and more variable than with different model initializations. Our work provides insights into the stability of flash attention, but further investigation is needed to conclusively link numeric deviation to training instability. Future research should explore how various optimizations impact numeric deviation and widen the scope beyond flash attention to investigate other training optimizations. Understanding training instability and developing proxies to address it is crucial for efficient and effective model training.